Hello, everybody. Welcome back. Today we're going to be looking at Unit 8.5, which is all about acid-base titrations, which we've actually already talked about if you watched my last video. Today's topic focuses a little bit more on the graphical side of looking at acid-base titrations, but it's also going to review some of the topics that we have looked at so far in this unit. So get your calculators out and let's get started. All right, so let's go back to the very first type of titration that we did, which was having a strong acid titrated with a strong base. And if that is the case, then this larger graph that you're seeing in front of you, that is what the titration curve would look like if you were monitoring the pH as you add more and more base. The graph on the right would be the exact opposite situation. If you have a set amount of strong base and you're titrating it with strong acid, you would see the same, the mirror image of that curve, but the pH would be decreasing because you're adding more and more strong acid. But these two curves have a lot in common, all right? So everywhere in the section here, I'm highlighting this for you, okay? Everywhere in that section, after some base has started to be added, but before we have reached the equivalence point, if you will recall what those, what I call Newman ice tables looked like, we had leftover H+, leftover strong acid, which is why the pH is below 7 everywhere in that zone. Whereas everywhere beyond the equivalence point, in that zone, we had excess leftover OH-, again, which is why you see the pH above 7. At the equivalence point, okay, for a strong acid, strong base titration, no matter which graph we're looking at, you will see that the pH is exactly 7 because all of the acid has been neutralized by the base, or vice versa. All of the base has been neutralized by the acid. So that is just something that is very characteristic of a strong acid, strong base titration. The pH at equivalence will be 7, exactly 7. Okay, then we looked at, this was the next type of titration that we looked at, and there was a whole lot more going on when you start bringing in something weak into the mix. What we looked at was a weak acid as our analyte. The strong base was our titrant, the one that we are adding progressively more and more and more of. And if you recall, if you watched the last video and you did the very long problem that calculates a pH all along this curve, before any base was added, the only thing present was the weak acid and water. We did a Wommack's problem and calculated the pH using the equilibrium expression. After base has started to be added, but before we reach the equivalence point, so I'm talking about this zone in here. If you will go back and look at the problems that we worked, everywhere in that zone, we did what I call a Newman ice table, where we reacted the weak acid with some of the strong base. Anywhere in that zone that I have highlighted there, what was left over at the end of that ice table was some weak acid and some conjugate base. And that area that I have highlighted there, guys, that is called the buffer zone, right? And if you recall, we found the pH anywhere in that zone by using the Henderson-Hasselbalch equation. And let's just point out a special place in that buffer zone. I can see that the equivalence point on this graph is reached when 50 mils of base have been added, which means that 25 milliliters, that is my halfway point or half equivalence point. And I just want to refresh your memory that at that place in a titration, it's sort of a special place, pH will be equal to pKa. Just wanted to remind you of that. So that is in that buffer zone, and that is actually where the buffer that's created is the most effective, is at the halfway point. Okay. At the equivalence point, this is where the calculations got quite long. Right? If you will recall, at the equivalence point, we did what I call a Newman ice table. And at the end of that Newman ice table, I did not have a buffer anymore. What was left over was conjugate base only. Okay, like for example, in this this graph, the weak acid that they're using as an example is acetic acid. And the conjugate base, that is the only part of at the end of the ice table, the only thing that is left over is that acetate ion. If you look back at the problems that we worked, what we did was we took that conjugate base, like acetate, we reacted it with water, running out of room here, and did a Womack's problem and ran equilibrium calculations. I want you to notice on this graph where the equivalence point is falling. It is greater than 7. And the reason that that is because look at this reaction that we just wrote here and look at what has been created. OH minus has been created. Okay, AC minus, that's acetate ion, that conjugate base, is a weak base. And it produces some OH minus ions, which is why you see the equivalence point in this situation above 7 in the basic range. Okay, so it's a really common thing for people to say, students to say, well, the equivalence point is greater than 7 because we were titrating with a strong base. Okay, and you're not wrong. It's just that that's not really exactly the reason. The real reason is because this reaction takes place at the equivalence point and OH minus is produced. All right, anywhere beyond the equivalence point, so in this zone in here, what ended up after our Newman ice table, we ended up having some 2 bases left over. Okay, we had some strong base left over and some conjugate base left over. And we look at both and we say, okay, which one is stronger? OH minus would be the stronger one. So we have excess OH minus. We used that to find our POH and then to our pH. So just reviewing this with you from last class and just showing it to you, all the calculations that we did, but in a graphical form. If we were going the other way, so we have a set amount of weak base, that's our analyte, and our titrant is the strong acid. We're adding progressively more and more strong acid. So at the beginning of this titration right here, we have weak base only. We did a Womack's problem. We used equilibrium to find the pH. Okay. Anywhere in this zone, okay, again, this is called the buffer zone. Why? Because now that we've started adding acid, we have a Newman ice table, and at the end of that Newman ice table, we see anywhere in this zone that I've highlighted that we have a buffer left over, and we can use the Henderson-Hasselbalch equation to solve for pH. Okay, we can see that the equivalence point is at 50, which means that at 25, this is our halfway point, or half equivalence point. You can call it either one. And just like on the graph before, at the halfway point, pH equals pKa. The only thing that makes this graph a little bit different is just that you are typically not given a Ka value. Typically, you would be given the Kb value for the weak base, but we have seen multiple times that you could use this equation to solve for the Ka and then use this relationship. Okay. At the equivalence point, right, we did a Newman ice table, and we saw that all that we had left over was excess conjugate acid. Okay, if I'm remembering correctly, I think the example we did in the last video, we had ammonium was the conjugate acid that remained, and we ran a Womack's ice table right underneath. It looked like this. Okay, and I want you guys, once again, notice where the equivalence point is. It's below 7. Okay, if you were asked to explain why that is, don't say, oh, it's because we were titrating with a strong acid. Here's the better explanation. The better explanation is because this reaction takes place. NH4 plus is a weak acid, and we're creating some H3O plus. That's going to bring that equivalence point down into the acidic range. Okay. And last but not least, anywhere beyond the equivalence point, so in this area, you would have, at the end of your Newman ice table, you would have some strong acid left over and some weak acid. It's not a buffer, so you would go with the excess strong H plus that would be left over and use that to directly find your pH. So I wanted to go over these graphs with you because very often, guys, you will be asked to draw a graph on the AP exam. And we're going to do one question together, and then I'm going to have you try one on your own. So let's look at this. It says a 30 milliliter sample of 0.05 molar solution of hydrogen carbonate, and then we're given a Kb value. So hydrogen carbonate is what we call amphiprotic or amphoteric. It can behave as an acid and a base. In this particular situation, we're going to treat it as a weak base. We're titrating it with 0.05 molar hydrochloric acid. Sketch the expected titration curve given the following information. We are given the starting pH, and we're given the pH at equivalence. Now, if you're going to sketch a titration curve, ladies and gentlemen, you really need 3 data points: the starting pH, the pH at equivalence, and the pH at the halfway point, which we have not been given. Okay, we need to find that. The other thing that we're not told, but we can figure out, is where are these data points going to fall on the x-axis? I need to, before I can even start plotting points, I need to see, well, okay, I know the pH at equivalence, but where should that be on the x-axis? Where is that going to line up? I need to solve for what volume of acid has been added at the equivalence point. Okay, so let's figure that out. First thing I'm going to do is I'm listing out my major species here. Okay, I know that HCO3 minus is going to serve as my weak base, and H plus, the king daddy of acids, that's the best choice for the acid. So here is my net ionic equation. Now guys, let's remember what it means to even be at the equivalence point. If you can find moles of one of your pieces in this picture, the acid or the base, you can use stoichiometry to find moles of the other one. And that's going to lead us to find the volume. So I was given all the information for that bicarbonate ion, 30 milliliters, 0.05 molar. I do a multiplication. That tells me that in this particular scenario, I have 1.5 millimoles of my weak base. I'm going to use stoichiometry to get to millimoles of my acid. It happens to be the same number. And from there, if you'll look back at the original problem, if I know the millimoles of the acid and I know the molarity of the acid, I can solve for the volume of acid. Now again, why do I need to know that? Because I need to know where to put that data point of the equivalence point on my graph, like where on the x-axis does that data point need to fall? Okay, so we were told that the pH at the beginning of the titration fell at 9 point something. I can't remember what the pH was. That was given to us in the problem. I just figured out that the equivalence point is going to fall at 30 milliliters, and we were given the pH at equivalence. The last piece to this puzzle was we need to find the pH at the halfway point. Okay, so I know since the equivalence point fell at 30 milliliters, I know that my halfway point is going to be at 15 milliliters. But remember, guys, we know a special relationship about the pH at the half equivalence point. It's equal to pKa. Now, we were not given a Ka. We were given a Kb. But I can solve for that Ka. Okay, pKa is nothing more than the negative log of the Ka. Remember this relationship, guys. So to find that Ka, I can do Kw divided by the Kb that was given in the problem, 2.3 times 10 to the negative 8th. And when you plug all of that into your calculator, the pH comes out to be 6.36. So that is the data point at the halfway point. So let's plot that. Okay. The last part of this is to simply sketch the curve. Okay, remember that the equivalence point is where the curve is semi-vertical. It's the most vertical part of the graph. And the halfway point is where your curve is going to be relatively horizontal. So I might draw something that looks like this. And then it levels out like that. So that is what would get you full credit. Let me say one more time, if you're asked to sketch a titration curve, you need to plot at least 3 data points. The pH at 0, the pH at equivalence and the pH at the halfway point. And you'll always be given enough information to find those pHs. So I want you guys to pause the video and try this. This kind of brings together things we talked about in the last unit and graphing in this unit. So give it a try. All right, let's check your answers. So we're given a situation where we have this weak acid, HY, and we're going to be titrating it with a strong base, sodium hydroxide. And the first part of this says, calculate the volume of base, NaOH, needed to reach the equivalence point. And so we're going to have to do a calculation very similar to a problem that we just did a minute ago, where we had to find the volume of titrant at the equivalence point. So for letter A, I did the same process. I wrote out my major species, I wrote my net ionic equation, and I was given enough information in the problem to find millimoles of my acid. I then used stoichiometry to find millimoles of my base. We were given the molarity of the base, and if I have the millimoles and I have the molarity, then I can solve for the amount. Oh, that's a typo. That should say at the very end, that should not say acid. That should say base. Okay, but that is how I was able to find the volume of base needed to reach the equivalence point. Part B said calculate the pKa for the weak acid, and that was pretty straightforward because we were given the Ka in the problem, so I just took negative log of that number, which gave us 7.75. Letter C said determine the pH of the original acid, meaning before any base has been added. So if you went through and you thought about, okay, there's no base, it's just the weak acid and water, it's a Womack's problem, this is what you should have ended up with. Okay, so that would be the pH before any base has been added, and the number makes sense because the only thing present is weak acid, so it makes sense that the pH is below 7. Okay, last but not least, they wanted us to sketch the titration curve. And guys, remember, you need 3 data points. The pH before any titrant has been added, the pH at the halfway point, and the pH at the equivalence point. And you need to know where the equivalence point should fall. So from previous parts, part C, we know that the pH before any base has been added, the pH is 4.37. There's our first data point. We know that the pH at the halfway point is equal to pKa, which we solved for in part B. We don't know the pH at equivalence yet, but I do know at least where that data point should fall on the x-axis, because from part A, we found the volume of base added where that is, at the equivalence point. Now we do need to solve for the pH at equivalence. And again, this is review from something we've done before, but let me pull up my work to solve for that pH. Okay, so there's a lot going on here. Let's talk through it. So at the equivalence point, okay, once we've started adding base, here is my net ionic equation. And it's definitely a Newman situation because there's no water on the reactant side. We're at the equivalence point, so I was given enough information to know how much acid there was, and since we're at equivalence, this number must be the same. Completed the Newman ice table, and I was left with conjugate base only. And it's a weak base. All that's left is Y minus and H2O. So what do you do in that situation? You do a Womix. But remember, guys, a Womix ice table needs molarity, not moles. So I had to divide by the total volume. Now, how did I know what that number should be? Well, in the original problem, we were told there are 50 milliliters of the acid, and in part A of this problem, we knew at equivalence that there would be 50 mils of the base, so I just added those together to get 100. Found the molarity of Y minus, and I plugged it into my Womix ice table here. Now, one thing that students tend to struggle with is at the end of these Womix ice tables, how did you know whether to make that Ka or Kb? How do you know which one to use? Focus on the species that is being added to water and ask yourself, what is that thing? Look at it from left to right. What is it doing? It's accepting a hydrogen ion. It is a base, which is why I needed a Kb value, which I wasn't given in the problem, but I can find it. We've seen that skill a couple of times now. I put it into my calculator. I graphed and solved for x, which I knew was equal to OH minus. I could then find the POH very easily, negative log of my hydroxide concentration, and then get to my pH. So now I have my third data point. So let's plot these points. So there is the first data point before any base has been added. Here is my halfway point. You'll notice, where does it fall on the x-axis? It falls at 25 milliliters. How did I know to put it there? Because from part A of this problem, I knew that 50 milliliters is where the equivalence point is, so 25 must be where I should put my halfway data point. And there is the pH at equivalence. The only thing that remains is I need to actually draw the line. Remember, equivalence point is where your curve is relatively vertical. Halfway point, your curve is relatively horizontal. So it's kind of like playing connect the dots here. I'm going to draw something like this. And then it just kind of curves off at the end. Okay. So I've said it a number of times, when you're asked to sketch a titration curve, you need 3 data points. At 0, the halfway point, and the equivalence point. And you'll always be given enough information to find those 3 points. The last thing I would like you all to do is just to look at a sample multiple choice question. So you're given a titration curve and you're asked something about different points along this curve. So I want you to pause your video and see if you can figure it out. All right, I'm going to talk through this one with you. Based on this graph and based on where the equivalence point is falling, I can see that this data point T is pointing to the equivalence point, and I can see that it is above 7. So this is telling me that this titration is a weak acid with a strong base. So I want us to think about what reaction is taking place at each of the different points in time. All right, so let's start with data point Q, where no base has been added yet. That means all I have is weak acid and water. So I'm going to write at data point Q, the only reaction that's taking place is what we would call a Wommack's problem. Okay, so that's the reaction that is occurring at data point Q. Now, data points R, S, and T, base now has been added. So I'm going to update my major species list. Let's say that the strong base that's being added is like sodium hydroxide. Once base has been added, let's think about what the reaction is that's occurring at data points R, S, and T. It's not a Wommack's problem anymore. It would be a Newman problem. And the reaction would look something like this. Okay, so that reaction that I just wrote there, that's what's taking place at R, S, and T. So I'm going to go a little bit out of order, okay? If you think about this reaction that's taking place at data points R, S, and T, think about your Newman ice table here. What would be left on the E line of that ice table at these different points? At data point R, that's the halfway point, I'm going to have a number left in this column. This column will be 0. We don't care about water. And this column will be the same number. At data point R, that's the halfway point, the amount of weak acid and conjugate base is equal. And when you put those numbers into the Henderson-Hasselbalch equation, that final term ends up canceling out to 0. So this question says, at which data point is the molarity of acid greater than the molarity of its conjugate base? It's not going to be data point R, because at data point R, these molarities will be the same. So that's out. At data point S, okay, I'm still in that buffer zone, but this number that's left in my ice table is going to be greater than that one. I'm still in the buffer zone, but I'm beyond the halfway point. So whatever number is left at the end here is going to be larger than this one. Let me take all that out. So it's not data point S. At data point T, that is the equivalence point. And both of my reactants are going to be left as 0. So the molarity of my conjugate base is definitely greater than the molarity of my acid because I don't have any acid. So that's out. So this is my answer, but I want to make sure you guys understand why. This reaction that's taking place there, remember the kinds of Ka values that weak acids have? They're very small. They're usually like, numbers like 1.8 times 10 to the negative 8th. They're very small, which means this reaction is proceeding very little in the forward direction. There's going to be very little amounts of A minus. There will definitely be a greater amount of acid, of weak acid, than there is of the conjugate base. And that's why data point Q is the answer. Another area where this would also be true would really be anywhere in this zone. As long as you're before the halfway point, those could also be possible areas where this would be true. So that's just a kind of possible multiple choice question that you could see. So that is it for Unit 8.5, and I hope that kind of brings things kind of all together for you. You know, it reviewed some of the types of calculations that we've done before, but it's also showing it to you in terms of a graphical setting. So I hope you learned a little something today, and I look forward to seeing you next time.